This conversation is generated under the StoreMore project. This project is supported by the Interreg Danube Region Programme, co-funded by the European Union. The content of this conversation does not necessarily represent the official position of the European Union.
Okay, so powering our lives reliably, it's getting trickier, right?
Yeah.
Especially now with more wind and solar. I mean, the sun doesn't always shine, the wind doesn't always blow. So how do we actually store that energy reliably and at scale?
Yeah, that's the big question. And it's not just technical, is it? It's economic, environmental. It's forcing us to look beyond the usual suspects for energy storage.
Exactly. Which brings us to today's deep dive. We're looking at something called liquid air energy storage. LAES. Sounds a bit sci-fi, maybe. Storing energy by chilling air until it's liquid. Super cold cryogenic temperatures.
You might also hear it called cryogenic energy storage, CES. Same thing, really.
Right. So our mission today is basically to unpack this, how it works, why it's potentially so valuable, and where it fits into the bigger energy picture. By the end, you should have a really clear idea of why LAES is suddenly a serious contender. Okay, let's get into it. So this whole idea, liquefying air for energy storage, how does it actually work in practice on a grid scale?
Well, fundamentally, it's a three-stage cycle. First, you've got the charging stage. You take normal ambient air,
Just regular air?
compress it, then cool it way down.
Right.
We're talking about minus 196 degrees Celsius. That turns it into liquid air.
Minus 196 C. Wow. Okay, so that's the cryogen part. And this uses electricity, presumably when it's cheap or abundant, like from Renewable.
Exactly. You're using that surplus power to liquefy the air. That liquid air then gets stored. Stage 2, it sits in large insulated tanks, kind of like giant thermoses at low pressure.
Okay, so you've basically bottled the energy as super cold liquid air.
Yeah.
How do you get the power back out?
Right. Stage 3, discharge. When you need the electricity, you pump the liquid air to a high pressure, then you heat it up, causing it to rapidly vaporize back into a gas.
And that expansion.
That a high-pressure gas then rushes through a turbine, spins it, and generates electricity. So you're essentially reversing the process, turning that stored cold back into useful power.
Okay, pretty neat physics. But beyond just being clever, what are the real advantages? Why LAEs compared to, say, giant batteries or pumped hydro?
Well, one of the really big ones is materials. Think about it. What do you need? Air, steel for the tanks, maybe some aluminum. These are abundant, right? Unlike some battery chemistries that rely on materials like lithium or cobalt, which have, supply chain and geopolitical issues.
Ah, so it's more about resource security and independence. That makes sense.
Yeah.
And the system itself lasts a long time, I read.
Yeah, that's another key point. These plants are designed for a long lifespan, like 20, 30, even 40 years. Much longer than many battery systems currently offer.
And I also picked up on the fact that you can apparently build these plants almost anywhere. They don't need mountains like pumped hydro does. Plus, they're scalable, from relatively small to really massive installations. High view power is building big ones now, right?
Absolutely. That location independence is, frankly, a game changer. You can put them near cities, near industrial sites, right where the grid needs support.
Yeah.
Yes, the scalability is huge. You can go from, say, 1 megawatt, enough for a small community maybe, right up to 10 gigawatts, which is serious utility scale.
Okay.
And there's another clever bit, waste heat integration. If you site a LAES plant near an industrial process that generates waste heat, or even use low-grade environmental heat.
You can use that heat to help vaporize the liquid air.
Exactly. A standalone LES plant might have a round-trip efficiency of, say, around 60%. That's the energy out compared to energy in. But if you integrate waste heat effectively, you can push that maybe up towards 70%. That makes it much more competitive, especially for long-duration storage, like providing power for many hours or even days.
Right, so it's good for more than just quick bursts.
Yeah.
Grid stability, handling peak demand.
Yeah.
That sort of thing.
Precisely. Ancillary services, peak shaving. It's well-suited for those grid-level jobs.
Okay, sounds pretty compelling.
Right.
But no technology is perfect. What are the downsides, the trade-offs with LAEs?
That's fair. The main one people point to is that round-trip efficiency. Even at 70%, it's generally lower than, say, lithium-ion batteries, which can be up in the 90s.
Okay, so you lose a bit more energy in the conversion process.
You do. And the upfront costs, the capital expenditure, can be significant. You're building a complex plant with cryogenic equipment, turbines, storage tanks. It's a big industrial project.
Right. But what about running costs?
That's where it balances out somewhat. Once it's built, the operational costs are actually quite low. We're talking maybe 1.5% of the capital costs per year. There aren't that many moving parts compared to some power plants, and your fuel air is free. So over that long 20-40-year lifespan, the economics start to look pretty good, especially for large-scale, long-duration needs.
Okay, let's try and wrap this up. So what does this all mean for you listening? We've looked at LAES liquid air energy storage. It seems like a really scalable, geographically flexible way to store energy for long periods. It uses common materials, which is a big plus.
Mm-hmm. Strategic advantage there.
Right. And leverages existing industrial tech, long lifespan, low running costs. The trade-off seems to be mainly that round-trip efficiency, which is decent, but maybe not best in class compared to short-term batteries.
Yeah, but often good enough, especially when you factor in the potential boost from waste heat and its suitability for that utility scale long-duration role, from 1 megawatt up to 10 gigawatts, remember.
So the real kicker seems to be that freedom from geography. You don't need a mountain, you don't need a specific salt cavern or anything.
Exactly. You can, in theory, build these almost anywhere the grid needs them. That really changes the planning conversation for large-scale storage deployment.
So here's a thought to leave you with. Imagine that. A future where storing massive amounts of renewable energy isn't fundamentally limited by where you are. Not by mountains or geology, but really just by our engineering ability to chill air down to minus 196 degrees Celsius. How might that ability to put large-scale storage almost anywhere? How could that reshape our energy grid? Maybe even influence where industries develop or where we choose to live? Something to think about.